Bismillahirrahmanirrahim. Assalamu alaikum. My name is Zuhanim, roll number 21 TE01. Today I will be discussing lab number 8 of digital signal processing. The title of this lab is Moving Average Filter and FIR Filters using the Fourier Transform Design Method. The objectives of this lab are implementation and analysis of moving average filter, implementation and analysis of finite impulse response filter Fourier Transform Design Method. In the task 1, it is a theoretical task. We are required to define a filter, define types of filters, what are the time domain and frequency domain parameters of a filter, and we have to discuss the role of a low pass filter for the filter designing. So for this, filter. A filter is a device or algorithm that allows certain frequencies or signals to pass through the while attenuating or blocking other frequencies. Filters are commonly used in signal processing to modify the characteristics of a signal, such as removing the noise or unwanted frequencies, emphasizing the certain frequencies, or shaping the frequency response of a system. For the part B, we have types of filters. Filters can be classified into several types based on their characteristics and applications. Some common types include low pass filter, allows frequencies below a certain cutoff frequency to pass through while attenuating higher frequencies. High pass filter allows frequencies above a certain cutoff frequency to pass through while attenuating lower frequencies. Band pass filter allows frequencies within a certain range bandwidth to pass through while attenuating frequencies outside that range. Band stop filter or notch filter attenuates frequencies within a certain range while allowing frequencies outside that range to pass through. All pass filter allows all frequencies to pass through but alters the phase relationship between different frequency components. Shelving filter boosts or attenuates frequencies above or below a certain frequency, often used in equalization. Here are the characteristics of different filters. First, the low pass filter, then the high pass filter, band pass, and notch filter or the band stop filter. The time domain parameters include fast step response, no overshoot, phase linearity. And phase linearity can be detected by using the slope on the falling and rising edges. Here is an example. Slow step response means the filter is poor. We should have a fast step response. We should have no overshoot and the phase should be linear. Now for the frequency domain parameters, we should have fast roll off, no ripples in the pass band, and good stop band attenuation. Here are some examples. Role of low pass filter for filter designing. The low pass filter plays a crucial role in filter designing because we can create all kinds of filters just by altering or modifying a good low pass filter. A low pass filter can be converted to high pass by spectrum inversion. Band pass filter can be designed using a low pass filter and convolving its output by its inverse, that is the high pass filter. Band reject filter can also be created by the spectrum inversion of band pass filter, or we can also add the low pass output and its inverse output in the parallel. Moving on to task 2, we have to plot the given signal in the frequency and time domain along with its magnitude response, and we then have to apply a moving average filter. And the part B, we have to apply a 3 tap, in C 11 tap, and in D part 25 tap filter. To see this code, we have this. Here we have created our signal, then we have added the noise to our signal, and we have defined the moving average filters. Then we have applied the filters to the noisy signal, and then we have plotted the signal in the time domain and in the frequency domain. To see the output, we have by looking at the output, we can see that when we increase the number of taps, we can see the smoothing effect. The transition rate in the lower number of taps is more, but the smoothing effect is more in the larger taps. So it's a trade-off between smoothing effect, noise reduction, and transition time. For task 3, we have to repeat example with a 7 tap, 17 tap, 51 tap, and 101 tap, and we have to observe the frequency domain parameters. We also have to apply the filter made in the first part to the signal given below and observe the changes. To see the code, we have Here we have defined our parameters and calculated the normal cutoff frequency. Then we have the number of coefficients for the different tap lengths, and we have calculated the filter coefficients. Then we have the transfer function coefficients, the frequency response, and then we have the plotting of the magnitude frequency response. Here we have a frequency response for the 101 tap filter. Then we have a 51 tap filter, 17 tap filter, and 7 tap filter, and then we have the 3 tap filter. Moving towards the last task we have to repeat the given example with 7 tap, 17 tap, 51 tap, and 101 tap, and we have to observe the frequency domain parameters. Then we also have to apply the filter made in the above part with the signal X and you observe the changes. For this we have defined all the parameters, then we have the number of coefficients for the different tap lengths, and we have applied the filters and to observe the changes. We use subplots to plot the different signals. We have calculated the filter coefficients and we have applied the signal to the filter to the signal. Here is the output.